If you discuss, see what is nano. So if you understand what is nano, nano means 1 billionth of a meter. That means if I want to define 1 nano, then it means that 1 nanometer is 10 raised to power minus 9 meters, right? So that's how small that unit is. Now, what is nanotechnology? So nanotechnology is science, engineering, and technology, which is conducted at a nanoscale. So from 1 nanometer to 100 nanometers, we will treat it as in nanoscale, and above 100 nanometers, we will treat it as a bulk material. Okay? The term nanotechnology was defined by a Tokyo University professor in 1974. Now, if you want to visualize how small that nanometer unit is, then see a human hair, and that human hair is approximately 60 to 80,000 nanometer wide. So one can imagine as to how small that unit is, right? Now, see that how they were discovered and all. So the first nano material to be discovered was a buckyball. It's a carbon atom ring. There are 60 carbon atoms ring, and it was discovered in 1950. Then we had carbon nanotubes, which were discovered in 1991. Then we have graphene, which was discovered in 2011, for which a Nobel Prize was also awarded. Then you'll see that when I reach from bulk scale or bulk material and I go up to nano scale, or macro scales, when I go up to nano scale, I will see that there are change in properties. The first question that arises is, what properties changes? What are those properties that change? Right? So the properties that changes are that the size dependent and the surface dominated properties change. So the first property that changes are the electrical properties, right? What is an electrical property? The band gap. Now, what is band gap? Band gap is the difference in energy level of the valence band and the conduction level, right? So if I take the semiconductor material, then you will see that as I take my semiconductor material to the nanoscale, the band gap would increase. Right? For example, if I take a gallium arsenide, if I measure its band gap energy in the bulk scale, then it is bulk material, then it is 1.14 electron. But as I take my gallium arsenide to nanoscales, then I would say that its band gap energy becomes 1.4 electron. So there's a jump in energy, the band gap energy. But if I take a metal, for that matter, then I will see that as I take my metal to the nanoscales, their electrical conductivity will increase. That means the band gap is decreasing. Right? So depending upon which material are you taking, whether you're taking a semiconductor or you're taking metal, the band gap would either increase or decrease. But the point is that the electrical property changes when you're taking a material from the macro scales to nanoscales. That is an important property. And this variation that when I take my material from nanoscales and I change the band gap, immensely used in nanoelectronics, and this property of changing of the band gap, the size, is what is engineering. A lot of research goes into band gap. Sixth property that changes are the optical properties. So the optical properties, what do you mean by optical properties? The amount of light, color of light that material would actually emit. So, for example, if I take a gold, the gold that we use, at the macro scale, and in the bulk form, that gold will appear to be golden in color. But if I take that material in the nano scales, then I will see that this color changes, and its color changes to red. In the figure also, you can see I have a quantum dot. Right? We'll discuss what a quantum dots are. And you can see that as I'm changing the particle size from 510 nanometer, 555, and 570, 90, and 650 nanometer, so on, I can see there's a distinct change in the color, right? From green to lighter green and yellows and oranges, and then red. As you're changing the size, you can see that there's a change in color that the material is actually emitting. So there is a change in the optical properties. When you take a material from the bulk, nanoscale, right? So the third property that actually changes is the melting point. Now you will see that this melting point actually decreases with size. So you can see also in the figure that on the y-axis I have a melting temperature and on the x-axis I have a nanoparticle size. And then as I'm decreasing the size of the particle, you can see that there is a drop and there is a drastic drop in melting temperature, right? That means as I decrease the size of the material and I take them to nanoscales, the melting temperature would also drop. Why does it drop? We'll discuss later, but for the time being, remember that with the size in the nanoparticles, melting temperature is decreasing. As an example, if you see that at the macro scales, gold has a melting point of 1000 degrees centigrade. And if you're decreasing the size to 10 nanometers and below that, melting temperature actually drops to about 100 degrees centigrade. So from 1000 degrees centigrade at the macro scale, it is actually dropped to 100 degrees centigrade. It's such a drastic drop. Melting point. Why does it decrease? We'll see. Time being, remember that the melting point actually changes and it decreases within that size. But at what scales? At nanoscales. That is important. Okay. Then we have the magnetic property. For magnetism, we know that the materials are there's a diamagnetic, paramagnetic, ferro, antiferro, ferri, and all those things there. But what happens when you take the material to the nanoscales? So when I take the material to the nanoscales, and if I see a hysteresis loop, what is a hysteresis loop? That I plot the graph between magnetization and the applied magnetic field. So there is a energy loss curve, that is what is called as a hysteresis loop. And you can see that as you decrease the size of the nanoparticle, and you take up to the nanoscales, that area of hysteresis loop actually decreases. That means that the energy loss actually decreases. And you expect the particle to become ferromagnetic at the nanoscale, but that doesn't happen actually. Like the particles become super paramagnetic at nanoscales. So instead of multi-domains, ferromagnetic as a material has a macro scale, at the nanoscales, you will see that they have single domains and they exhibit super paramagnetism. So they're aligned in the direction of the magnetic field and they form single domains, not multi-domains, as in ferromagnets, right? The materials, the nanomaterials, they actually become super paramagnetic. So there's a change in the magnetic property as you take the material. Then there's a wettability. What is wettability? Wettability is actually the contact between of a liquid with a solid surface, right? So if a liquid makes a complete contact with the surface, that means it is wetting it, right? So that is what is wettability. How much it is wetting would be wettability, right? So wettability of any material is measured by its contact angle. So you see that the contact angle increases as you move to nanoscales, right? You can see also here in the figure, for the bulk, you have a 0 degree contact angle. As you're decreasing the size of the particle, you're saying that the contact angle is increasing. And because the contact angle increases, the wettability would decrease. And that is primarily the reason why the nanomaterials are hydrophobic in nature. And this is the property that because the nanomaterials are hydrophobic, so this property is used in so many different applications of nanomaterials and nanotechnology. There are fabrics out discussed in later slides. But for the time being, making fabrics of from the nanomaterials because of their hydrophobicity, and that is because the contact angle made by them is large, and hence the wettability is lesser. Okay? Then, question is, why are these properties changing? Right? So why are these properties changing is the question. That there have to be certain changes when you're taking the material to nanoscales that the properties are actually changing. Okay? So we discuss about the first property, and that is what is called as quantum confinement. So what is quantum confinement? So quantum confinement is observed when the size of the particle is too small to be comparable to the wavelength of the electron, right? So when you decrease the size of the particle you take particle size to as small as the wavelength of electron, is when particle is quantum confined. So what is quantum confined? By words, confinement is actually restricting the motion of the particle, right? It's restricting the particle. And quantum means that you're taking it to atomic scale. So when you are taking the particle and you're confining its motion to the atomic scale, that is what is quantum confinement. But what happens when you take the particle to restrict the motion at atomic scale is that the continuous level of energy that you get, continuous band that you get, that actually changes to discrete bands of energy. Right? So as a size of particle, there is a discreteness in energy which is observed. So as you take the particle to nanoscale, the energy level becomes discrete, and that actually increases for widens of the band gap. So you can see also in the figure that here in the bulk material, I have a valence band and a conduction band. There is a band gap. I'm decreasing the size. You can see that there is a discreteness, right? I have levels of energy. I get the levels of energy equals to 1, 2, 3, and 4, so on. I further decrease the size. Again, I get discrete levels of energy. Can I decrease the size? Again, I get more discreteness of energy. Whereas if you're decreasing the size of the particle, there is discreteness in the energy level which is observed. And this is primarily what is called a quantum confinement. So you decrease the size of the particle in such a manner that it becomes comparable to the wavelength of electron, as a result of which the energy levels become discrete. Then you have different nanoparticles it's exhibited. So you have a zinc sulfide, cadmium sulfide is there, and all those and all sorts of nanoparticles, and they've actually depicted the band gap energy. Okay? So you have 3.7 electron volts for zinc sulfide, and for Ag2S you have 0.9 electron volts for the. But this is an important property, quantum confinement, and that happens only at nanoscales. Okay. Then the second property that changes is the surface to volume ratio. You can also imagine and you can also visualize that when I decrease the size of the particle, if you keep on decreasing the size of the particle, what happens? That there are more particles at the surface of the particle. I will have more atoms on the surface than I will have in the volume. So what happens is that the surface to volume ratio would increase. Okay? So with the decrease in the radius of the sphere, you see that the surface to volume ratio increases. You can see also here that the volume of the sphere is 4 by 3 pi r cube. The surface area is 4 pi r. Right? So if I take the ratio of surface to volume, I will have 3 by r. That means if I decrease the size of the particle, surface to volume ratio would increase. Right? So I will have a greater portion of atoms at the sphere than I compare it to volume. Okay? So a particle of size 3 nanometer will have 50% of atom on its surface. A 10 nanometer particle will have 20%. And as you go increasing the size, the number of atoms on the surface will decrease. They will then occupy the volume. It's also a beautiful example of a cube. Divide the cube into smaller cubes, and you can see that there is a change in the surface to volume ratio. But what is the impact of actually increased surface to volume ratio at the nanoscales? Is that makes the nanoparticles more chemically reactive. Okay? And so you can see that because you have more atoms on the surface, they're actually more reactive, right? So materials which are actually inert in their bulk form is very reactive when they are taken up to nanoscale, and it's primarily the reason because of the surface to volume ratio. Also remember, previous slide we discussed that the melting point was actually decreasing with size. That is because of the surface to volume ratio was increasing. You have more atoms on the surface, right? So you need to supply only very less amount of energy to melt it. All the atoms are on the surface. That is the reason why melting point actually decreases when you are decreasing the size of the particle, but that only at nanoscale. That is what you mean. Okay. So we have now classification of nanomaterials, and we classify the nanomaterials based upon their dimensions. Okay. The first is we'll classify it. First, I have a zero dimension. Zero dimension means that all the dimensions of the particle will now be in the nanoscale, all dimensions. So this is a quantum dot. all the dimensions of the particle, x, y, z, all of them have been reduced to nanoscale. Okay? Then I have a one-dimensional nanomaterial, quantum wires, where two of its dimensions are within the nanoscale. For example, either a nanofiber or a nanotube. Okay? So this is a quantum wire. One of its dimensions are within the at the macro scale, or for in other words, two of its dimensions are in the nanoscale. Then I have a two-dimensional nanomaterial or a quantum well, where one of its three dimensions are within the nanoscale. Example, graphene. It's a 2D material, right? Then you have a bulk where none of its dimensions are within the nanoscale. Okay? So you have a zero-dimensional nanomaterial as quantum dot. You have one-dimensional nanomaterial as quantum wire. You have a two-dimensional material as quantum well, and a three-dimensional that is bulk material. So what is the density of states? So density of states is actually the derivative number of states with respect to energy. So how many level of energies of states actually are present for unit energy level is what is called as the density of states. Okay? It's a very famous curve that you always, when you talk about classification of nanomaterials, you say always asked to plot the density of states versus energy. So you can see the density of states versus energy for a quantum dot, for a quantum wire, for a two-dimensional quantum well, and for a bulk material. Okay? So this is density of states, dE, and E is the energy. So how many level of energy are present? How many levels or number of states, for example, for that matter, are present for unit energy level are the density of states. Okay. Then we come to the synthesis of nanomaterials. So there are actually two approaches by which you can synthesize a nanomaterial. One is called the top-down approach, and the other is a bottom approach. Okay. So in the top-down approach, you have that is called is actually a physical method. What is the top-down? Top-down method means that you start from the top and you go up to the bottom. That means that you start from a bulk material, you break it down into powders, then you break it down to nanoparticles, clusters, and that. Okay. So take a bigger material and you keep on breaking it up to that is a top-down approach. Breaking down a bulk into nano-sized structures. What's the disadvantage? That there's an imperfection on the surface. Okay. Whatever nanostructures you prepare from the top-down approaches, you will get they're actually imperfect. A lot of imperfections. Some of the techniques top-down approach are actually electron beam lithography, aerosol, and gas-based ionization are all top-down approaches. Okay, then we have a bottom-up approach. Bottom approach is bottom-up, means starting from the bottom and you're going up. Right? So you're taking the atoms, you condense your fusing them and all, and they're in clusters, and then particles and particles, and particles. That is how you synthesize bottom-up approach. So it's a physical and a chemical method. So you build atom by atom, you build a molecule by molecule, and you build cluster by cluster. It creates less waste, that you can see. And some of the methods that are there in the bottom approach are chemical vapor deposition or a plasma enhancing, and other CVD methods. They're all bottom approach. So you take from the atom, you go up to nanoparticles. Top-down approach, from the bulk, you go up to atomic scale. Okay. So we'll discuss bottom-up approach, and one of the methods is a chemical vapor deposition. So what happens is that there's a parent to family of processes whereby a solid material is deposited from a vapor form by the chemical reactions occurring in the vicinity of a normally heated substrate surface. The resulting solid material is in the form of thin film, powder, or a single crystal. So what is it? So you have a substrate, you take a catalyst particle, you take all sorts of gases, you have your hydrocarbon gas, which is that source gas, you have your inert gas, for example, hydrogen, neon, and all those things. Then you have a carrier gas also of hydrogen. Then you heat the furnace. Okay, when you heat it, what happens? All gases will break down. You will have atoms and you will have radicals. Radicals, they via surface and bulk diffusion. They actually diffuse into the substrate particle and you get the desired nanostructure. You can actually process the parameters, external parameters, and get the desired nanostructure. But what is important is that from the gaseous state, you're reaching up to nanoscale. Building the nanoparticles, atom by atom, cluster by cluster, and molecule by molecule. Okay? So this is actually a CVD method for carbon nanotubes. Okay. So here you can see we have a catalyst, all those radicals come in and they keep on diffusing and you're getting the nanotube. So this is catalyst particle at the base. You have a catalyst particle at the top. That is to the interaction of the substrate and the catalyst. Okay. But this is the method. Okay. So from the gaseous stages, you're reaching up to nanoscale. Right? So from the atomic, you're breaking down the gas with the help of an external source, and they're diffusing into the catalyst particle and giving you the desired nanostructure. UVD is a bottom-up approach. Right? Then we come to applications of nanotechnology. So you have nanotechnology, the various a wide range of applications of nanotechnology. They use in energy, they use in medicines and drugs, they use in nanobiotechnology, they use in devices, they use in optical engineering, using them in defense and security, using them in bioengineering, cosmetics. So one by one, we'll see all the applications. Okay. First is the use of nanotechnology in medicine. So, biomedical is for making biosensors out of detecting chemicals, using them as regenerative medicine. Why do you use all these things? Because they're more visible, they're rejection resistant, and artificial tissues and organs can be created out of nanoparticles. Okay? So huge amount of research goes into studying the nanomedicines nowadays, and this drug delivery system is actually very advanced. Use nanoparticles for drug delivery systems. And why do you use it? Because you see that the tissue and the organ, we are at the cellular level, right? The atomic level. Also, your nanoparticles are the same, so that absorption is faster and you can deliver the drug more efficiently by when you use a nanoparticle for delivering the drugs. Okay? Then you see also that the silver nanoparticle is an antibacterial effect, using all those things also in medicines. Okay? So there is nanotechnology is widely used in medicine area. Then the need of nanotechnology in electronics. So you can see nowadays we have all microelectronics using for many years now, but they've actually not solved the problems. The exceptional actually disadvantage of microelectronics are the physical science and the increased cost of fabrication of circuits. So nowadays, what we want is compact sizes of our electronic structures and as thin as they're possible. For advertising about the slimmest phones and thinnest phones and this resistant, that resistant. No, all those things they've not been achieved by microelectronics. So we shifted our gears to technology and we come see that material is advantage. So nanotechnology in electronics is the use of nanotechnology of electronic components, especially transistors. They're often referred to transistor devices that are so small that the interatomic interactions and quantum mechanical properties are studied. Okay? So besides being actually small and allowing more the nanos to be smaller sizes, actually package more transistors into a single chip. The uniform and symmetrical structures of nanotubes allow a higher electron mobility, a higher direct constant meaning the frequency, and a symmetric electron characteristics. All the features that they couldn't actually achieve by using microelectronics, we have achieved it by using nanomaterials in electronics. So nowadays we have nanotransistors, we have organic light emitting diodes, OLED, and have nanodiodes. So we're shifting actually to nano electronics, and whole entire bunch of engineering is actually been devoted to nanoelectronics. And you can see in national defense also we use nanotechnology. Why do we use it? Because see, it's actually very strong. And besides being strong, it is very light. So you have a lighter material which is strong, obviously you're going to prefer it compared to a heavier material which is strong, right? So I need to wear fabrics, defense personnel, so that matter needs to wear fabric which are lighter, right? Because they can withstand all the different weather conditions. So we need armor that they can actually withstand actually extreme conditions, weather conditions. See a nanotechnology, the nanomaterials are stronger, they're lighter, they're hydrophobic. Okay, so we're making fabrics and materials for the defense personnel using the nanomaterials. Then they're using robotics, they're using security, they're using detection, defense, and development of weapons. You have fuel economy, soldier protection, stealth movement, and for their health, the nanomedicines, and also for diagnosis of diseases also. For diagnosis also, nanomaterials. So using nowadays, so this armor thing is very much more important. Diagnosis and medicines. Okay. So using nanotechnology, defense and security area. Okay. Then we have use of nanotechnology in cosmetics. So what happens is by using it, but you can imagine that whatever cosmetics or whatever external application we apply to our faces and all, we apply it so that there is a faster. We want the material to be absorbed faster and stay long for a longer duration of time. You don't have to apply the material again and again. And that can only happen when it is absorbed, right, properly into your skin. So you have a nanoparticle and you have your skin. Both are at the same level, both are at the same atomic level, you absorb faster. That is the reason why, nowadays the sunscreens, they're actually come with this titanium dioxide or zinc oxide nanoparticles for their fast absorption, right? You have this mascara which is has a hyperbranched polymer nanoparticles for the longer, they don't smudge, right? Then you have perfumes and your perfumes actually have nanoparticles and emulsions, so the smell stays longer. You have the anti-acne treatment by using nanotechnology. You're protecting your hair against the ultraviolet rays. You're using hair restorative treatments. You're using a hydrogel face mask, and you use anti-aging creams. Okay, in all those things you have nanoparticles. So you're actually using all those properties of nanoparticles for their cosmetic uses, for defense uses, for electronics, and all sorts of areas that you can do. Then one of the nanotechnological applications is in fabrics. Okay, so if you remember in very early presentations on slides, we actually talked about wettability of and then I discussed the hydrophobicity of. So what happens is there is nanomaterials. The property of a new material are being treated size companies to performances as compared to conventional materials. For example, smaller clothing manufacturers are making water and stain repellent clothing using a nano-sized viscose. What happens is in normal fabrics, you use a nano-sized viscose. What happens is that the water is not going to stick onto that fabric, and the fabric is not going to get wet. Okay, so it's a hydrophobic material, and that causes the water to beat up on the surface. You can see in the figure, the water is not sticking up to the fabric, just beads up, right? So it is not wetting up the fabric. In using this manufacture the bulletproof jacket. So what happens? You're making it spill and dirt resistant, antimicrobial and antibacterial effect. It's amazing. There's a shark skin effect which is there, which all these swimmers nowadays they wear fabrics made of nanomaterials, so the water actually doesn't stick up to their clothing. So that is what is called the shark skin effect is there. So use nanotechnology in fabrics. We also use nanotechnology in biomedical there. So we have nanomedicines are there. Okay, you have biological names. This is you can see that there is a kidney chip. This is a liver chip. This is a lung chip. Okay, so all sorts of for different organs, making chips and all. Then you have bioinformatics. Okay. You have a biological 3D printing is there. Okay, so that is there. Then you have tissue regeneration. Okay. So different. Supposing person is with an accident or all, and his tissue gets damaged, so you can actually regenerate tissue with the help of. You have nanobiomaterials are there. Okay. Then using in cancer nanomedicines, nowadays we see a lot of people reporting cancers and all, suffering from it. So making nanomedicines out of the particles and because they're absorbed faster and all these things are there, and an efficient drug delivery from the nanoparticles is the cancer can actually be treated effectively with the cancer nanomedicine. Then we also use them in nanoscale imaging. Okay. So these are all actually the applications of biotechnology. Okay. So in this presentation, we actually first discussed as to what is a nano scale. So say that up to 100 nanometers, we take it as a nanotechnology, up to nanomaterials, and beyond 100 nanometers, we fine. Okay. So we visualized how small that is, and we see that a human hair, that thinnest thing you can visualize, that is actually 80,000 nanometers wide. So you can see how small that is. Then we discussed about what are the properties that are changing when I take my material from bulk to nanoscale. So we see that the electrical properties change, the optical properties change, the magnetic properties change, wettability change, and the melting point. Then we discussed as to why are these properties changed. Okay, so two most important things that happen is the quantum confinement and surface to volume ratio. So we see that when I take my material from bulk scale to a nanoscale, the particle gets quantum confined, and with the discreteness in energy observed. So by varying the size of the particle, you can engineer band gap, and that is what is called as a band gap engineering. So we said, see that the surface to volume ratio actually decreases. So the surface to volume ratio actually decreases. That means the particle becomes far more reactive at the nanoscale. Then we saw the classification. So we see a quantum dot, a wire, well, and fun. We saw the plots of density of states. Okay. Then we discussed about the synthesis of nanomaterials. So we discussed the top-down approach. We discussed the bottom-up approach. So in the top-down approach, we'll see that from bulk material, you start with from bulk material and you go down to the atomic levels. And in a bottom-up approach, you take up from the atomic level and you go up to bulk for the nanopart, crossing the nanoparticle realm. Then we discussed about the chemical vapor deposition, primarily for nanotubes we discussed in here, but that is in basic, that is what happens. When you take up gases, breaks them into radicals and atoms, and they get diffusers into that particle, and you get to desired nanostructures. Okay. Then we discussed about the applications of nanotechnology. We discussed in nanoelectronics. We have discussed it in defense and security. We discussed the applications of nanotechnology in medicines and drugs, in optical engineering, defense security, bioengineering, cosmetics, and nanofabrics. Okay, so this was a brief presentation on technology. I hope it helps in understanding a bit of nanotechnology. Thank you for your time and patience. Thank you.